wanted to introduce myself at the beginning. You most likely know me as Radeusz than by my real name. You might know me from Code Forces or Top Coder or some other competitions, which I was pretty successful in. I started my competitive programming career like 10 years ago, I think, or even more. And in the opposite to the previous speakers, I'm not a representative of ICPC, so I won't be able to show you any explicit data, but I will be able to share my experiences with you. And when Christian asked me what do I want to talk about, I was thinking about it. I wondered, wow, oh no, okay. What have I learned and I want to share? And I think I learned a few things. First, I learned that nobody is a genius. So when you reach a certain level of any skill actually, and it can be competitive programming or chess or anything else, you start understanding that everybody is just really, 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 really good, and just the number of repetitions of the word really goes up, and everything is achievable but by practice, but I won't talk too much about it. People think very differently. I'll address that a bit, but it won't be the main topic, and hopefully I learned how to practice, which will be the point of my presentation. So if you've ever asked any other competitor better than you how to get better, then the most likely you received answer solve problems, okay, which is actually true. But I think that something more could be said there. I think that at the period of my fastest increment of skills, I had some routine, some tips to share, and I kind of analyzed various scenarios where somebody, in my opinion, could have had all the skills or tools to solve a problem, but didn't do that. So that's something that we want to prevent, right? We want to be better at practicing. We want to not repeat our mistakes. And I think I managed to classify 2 mistakes that people do, and I try to present them to you. But they are pretty abstract, of course. I won't give you a golden formula to success. So we'll need some tools to show that abstract concepts. Oh, and also you can get better in a few different ways, like get better coordination with your teammates, but that's also different. Okay, so as for solving the problems, I wouldn't be myself if I wouldn't try to solve some problems with you. So we can start with the first one. So given a tree, we have to process queries about adding values to paths or subtrees, and queries about finding maximums on paths or subtrees. So if you're an experienced contestant, then you might immediately spot how to do this problem. You use heavy light decomposition to solve this problem. How exactly do you do that? It's not important for now. It's important that you do heavy light decomposition. So we can ask ourselves a question: what is a heavy light decomposition? I didn't intend the captions to slide in, but okay. So what is a heavy light decomposition then? Looking at the previous problem, we might suggest an answer that it's a tool to add its paths and subtrees and look for maximums then. But it's not a perfect definition. We can easily challenge it with the next problem. And the next problem is that we are given a tree. We have to modify the values written in the vertices, and we are asked about finding greatest common divisors of values on paths or subtrees. And how do we solve this problem? Well, we also use heavy light decomposition, oh no, something's broken, sorry. So what can be a heavy light decomposition then? Maybe it's a way to apply data structures to trees instead of arrays. But this definition also can be challenged with the problem C, which is a bit longer, but it's nice, so I read it quickly. So given a tree, we are allowed to like perform movements of the numbers written in the vertices. So we can choose a path like from the root to some vertex and shift it in a circular manner. And we have to, like, in a limited number of operations, make each number go to its specified vertex. And if you are a very good competitor this time, or you can extrapolate from incomplete data, you can probably expect that you solve it with heavy light decomposition. And it's not very important how exactly you do it, but the important thing is that you actually don't use data structures. The important thing is that you only use the partition of the tree into paths. That's only the fact that each vertical path in a tree can be split into a log of heavy paths is important for you. So, oh no, again. So maybe heavy light decomposition is a way to partition a tree into paths. Okay, so which of those definitions is correct? In my opinion, it's all of them, and it depends on the problem that you want to apply the heavy light decomposition on. So with those three ideas, which one should we be most focused on when we are like practicing? Maybe on the first one because it allows us to solve new problems. Maybe on the second one because it gives us an intuition, and maybe on the last one because it speeds us up. So in my opinion, it's very important to be at least aware of all of them. Like people tend to focus only on the last ones and forget about the basic building blocks that build the algorithms that they use, in this case, the partition in the paths. Okay, so how are you supposed to practice or analyze the problems that you've solved or didn't solve? So, in my opinion, you should build something that we can call solution anatomy, or actually coming up with a solution anatomy. So, you're supposed to build a directed acyclic graph of ideas or steps or conclusions that you made of simpler ideas that leads you to solving a problem. And it's, as the crossed text says, it's very important that it should suit you. Like it has to be realistic. It has to be like some way of thinking that could really happen for you during the competition. Like it doesn't have to be very likely that you do that, because, for example, if you analyze a problem that you didn't solve, then you didn't solve it, it didn't happen. But it has to be realistic. And doing that would be very helpful. I think people usually do it intuitively. They don't focus on this order of ideas and how do they come with each other. But like creating that thing and naming it allows me to like name those two mistakes or issues that I mentioned. And the first of them is what I showed with the heavy light stuff. I called it like a path contraction. It's when there's a sequence of steps that you see very often following each other, so you forget about the cases when you can apply them separately or mixed in some different conditions with different steps, like with heavy light decomposition, right? And actually, it doesn't have to be only a path. It can be a subgraph, like however you imagine your way of thinking. And what you are supposed to do is not to like always focus on the simplest, like most decomposed version of the graph, or only on the most composed way, because of the previous slide. Like each way of thinking about the steps benefits you in some different way. So in a perfect condition, you should be aware of the like decomposing steps that you can do, or all the contraction steps. but like forgetting about some versions of the graph might cause you to not solve a problem. I mean, not come up with a solution at all. Okay, so that's one thing that I've realized people, and also me sometimes, of course, tend to do badly. And I can also show you a second thing, which will require a different problem. So problem D says that given A and B, we have to compute A to the power of B, which is, I guess, a very easy problem. And if I ask anybody about the solution, then most likely I'll get this answer, and that you know this since you were like a child or something. So yeah, most likely I would also answer in the same way, but then we are given a bit harder problem. Like given K, we have to construct a graph with exactly K independent sets, and then we don't know what to do. So maybe analyzing the problems from the past a bit better would be more benefiting for us. So let's try to analyze this problem. So we can easily compute something for K equal to 0, right? Because we can compute A to the power of 0, which is 1. Having something computed for K, we can compute it for K plus 1, which is easy, it's multiplying by A. Having something computed for K, we can compute it for 2K, which is easy, it's squaring. And in a tricky manner of operations, we can compute something in log of n steps, right? So it's basic. I guess everybody here knows how to do fast exponentation. Okay, but we can now try to analyze the next problem. So an empty graph has only one independent set, right? If we add an isolated vertex to a graph, then the number of independent sets multiplies by 2, because the new vertex can be in an independent set with everything. And if you add a vertex connected to everything, it increases the number of independent sets by 1, because the new vertex cannot be with anything else in an independent set. So we can definitely see some correlations between those two problems. And still, knowing the first problem, you might not be able to solve the second problem. And why is that? And that's something that I this time wanted to call input labeling. So during the building of this graph, I think it's very important to focus on individual steps, like what conditions do need to happen to be able to do some transition in the thinking process. And why do I think it's that important to like name them explicitly to yourself? Because when you start working on the previous problem, the one with the graph, you don't immediately know that adding isolated vertex does something and adding something does something, but you might try one of them. And for example, you might try adding isolated vertex, and then you only have one operation of the mentioned one. But because you named all those 3 steps loudly to yourself, you hope that your brain will suggest that you are looking for the missing part, and will suggest you to keep in this way and try other operations that you can do on the graph. Or if you try the opposite, you try adding vertex connected with everything, it will behave in this way. And if you practice more and more, then you actually aim into this, that if you simply read the problem, you know that you are trying to reach something that is parameterized by n, then you hope that something will alert you that you are looking for an operation which add 1 and multiplies by 2. And if you are a very attentive listener, you might notice that this labeling from the slides is really not perfect, because I think in a perfect conditions, it shouldn't be from k to 2k, but it should be from k to any constant times k. And why is it important? Because looking at this, if in the future I will be in a conditions when I will have an operations which multiply by 3 and add 1, then something might not alert me, as I didn't specifically told myself that multiplying by some other constant would also work. So yeah, I think that labeling the inputs of tricks or steps is also very important and would allow to avoid not solving a problem or not coming up with a solution. Okay, so I guess it kind of explains what I meant with the title. So by don't copy ideas, I mean not focus on the whole DAGs that represent them, but focus on the interesting subgraphs or parts that happen in them, not only on the individual steps, but also on the subgraphs that are like contractible, and you can apply them or do a like sequence of steps in at once. And why? Because no two problems will be the same, so you are not supposed to know exactly how to solve the problems from the past, but you are supposed to extract tricks from them. And here, like hints what to do. So build this DAG of way of coming up with a solution, which should suit only you. Like it can be different for everybody, but you really have to imagine a way of you coming up with a solution to some problem, which usually is really possible. Like you don't have to only read an editorial and it should be done in this way, but it really adds a lot if you like try to figure out the conditions, what were you supposed to think or how were you supposed to think to actually solve it during the contest. And actually spending time on this, in my opinion, is very important. Like I remember having this routine of not only reading the solution, but wondering what went wrong. Like why didn't I solve this problem? What would be like my optimal way of thinking now that I know all the conditions and I'm after the contest? Which is of course easier to analyze problems that you haven't solved because you want to be better, but not disregarding the problems that you solved is also important because, for example, they might have different solutions than yours or might have some different observations which might also be useful for you. And authors post problems because they usually like them for some reason, so it's also nice to discover those reasons and maybe learn from them. Pay attention to those two issues or mistakes that I told you. And practicing because like dealing with this DAG of conclusions is not that easy, and I think that it's not always easy to avoid those mistakes that I mentioned, like doing the slideshow. Like 1 hour after sending it to Christian, I realized that maybe replacing the constants by would be a better move, but it's also teaching me something. So that's nice, and I think that speaking with others is also very beneficial because speaking with others and sharing your thoughts or experiences about problems, like shows you how people perceive the subgraphs from their ways of thinking. So that's why trying to spot that in their way of explaining problems is also very beneficial. And using like fortunately we have sources for sharing, like code forces, which I of course very recommend. And that's it from me. So thank you very much. Are there any questions?
Yeah, I think I turned it off. Okay, great. Just like a quick question on you. I mean, it's a reference to, well, you mentioned like nobody's a genius. So I want to go back to that point and really address one thing. So like, for example, just imagine for now, with the LLM development and these things, I think it's actually proven to be more true than before. Do you believe that if someone solves, let's say, 90% of the questions or more in code forces or any of the other AdCoder and these things, do you believe that they can actually grind up to like a 3,000 level, or is there somewhere where you see that like it's more of an inspiration and you have to actually connect the dots?
So the question is if I think that if somebody who solved 90% of the questions can grind up to like having legendary grandmaster title or something like that. I think it might be very hard to solve 90% of the problems and not reach LGM, but I think it might be possible, especially with AI now, which allows you to kind of like skip the learning process and so on. But that's an open question. I think that the tips from me are supposed to like boost your learning process and make it more efficient, but I think that even just by solving the problems and not paying much attention to analyzing the solutions and so on, you would also learn. So I think that just by solving 90% of the problems, you would also achieve the high ranks.
It's in reference to obviously LLMs that are developing and these things. So like they claim that so and so based on practicing on some data set, they can improve the rating to like 25, 26, and I think it's going up only. So I'm just wondering if there's an innate limit that you see. That I guess the person like me, yeah, I can believe that like you can go to 3,500, sure, why not? But like you may see differently, as in there might be some limit where like a grinding actually cannot push the envelope of the boundary, right? Is that like where do you see? Just curious about it because people have different opinions regarding that. Yeah.
I don't know much about like only grinding, as you call it, as I always try to. I try to be like rigoristic about my routine of after the contest analysis. So I think I won't be able to tell much about like only grinding experiences, and I don't think that anybody actually does the only grinding experiences, maybe except for the AI models. But I think if we are human beings, we actually like try to think what went wrong from time to time.